Welcome to the third lecture in this 8th module. As you'll recall, in the first two lectures, the first lecture I talked about point estimation and confidence intervals using t-distribution. And then in the second lecture, I talked about hypothesis testing for single group means and for mean differences, again, using the t-distribution. Now in this third lecture, I'm going to continue talking about hypothesis testing, but now we're going to talk about testing for the difference in means in two independent groups, and then also in 3 or more groups, and that will be using the F distribution and a procedure referred to as ANOVA. So let's talk about hypothesis testing for means in 2 independent groups. And so our objective here is that we want to know whether there's a difference in the means or averages between 2 separate groups in the population, but we want to know that difference based on the sample means that we have available to us. And so the mean sample difference would be symbolized by x bar for sample 1 minus x bar for sample 2. And so the assumptions for generalizing, we have some assumptions here for generalizing from the sample group means to the population. And these are the assumptions we're making. First of all, that our samples are independent and random samples. Secondly, that the population means for both groups from which the samples are drawn are normally distributed, or that they have a sample size of 30 or greater based on the central limit theorem. And then thirdly, that the population variances for both groups from which the samples are drawn are equal. And this assumption, however, can be ignored if the 2 sample sizes are equal. But this assumption is important, this third one, and we'll see why here in a minute. Okay, so when it comes to formulating the hypotheses, there are 3 different kinds of hypotheses we can have. The first would be there are 2 different kinds of one-tailed hypotheses and then one two-tailed hypothesis. So our one-tailed hypothesis would be our alternate hypothesis, if it's one-tailed on the left side, would be that population mean 1 is less than population mean 2. The null hypothesis, which is the mutually exclusive alternative, is that the population mean in group 1, population 1, is greater than or equal to the population mean for group 2. The one-tailed hypothesis on the right side is just the exact reverse of that the population mean in group 1 is larger than that in group 2. And then our two-tailed hypothesis is simply that the 2 population means are not equal. We're not specifying whether they're less than or greater than. And then the null hypothesis is that they are equal. And so in this case, what we actually do is called a pooled t-test. And so again, we're using the t-distribution, which we discussed before and which you're familiar with by now. And so this t-test, the formula is shown down there. And so the numerator of the t-test is quite simple. It's just sample mean 1 minus sample mean 2 minus 0. In the denominator, though, we have the pooled standard deviation multiplied by the square root of 1 over sample mean 1 plus 1 over sample mean 2. And so there are a few things to note about this that are different. One is just how do you calculate that pooled standard deviation. So I've shown the formula on the bottom of the slide there, the bottom left. And so you can see it involves a square root. It's complicated looking, but it's really not that difficult. As long as you have the sample size N1 and N2, and then the sample variances, S1 squared and S2 squared, it's pretty easy to calculate that formula, right? It just looks complicated. Interestingly, the entire denominator that you see there for the pooled t-test is also equal to the pooled standard error. You can see the formula at the bottom there. The other thing to note on this page is that the t-test is associated with certain degrees of freedom, and that's why that N1 plus N2 minus 2 are there in the subscript. And those are the degrees of freedom for both groups together. So we're just adding the sample size for both groups, subtracting 2, and that gives us our degrees of freedom for the pooled t-test. And so that leads us then to this recipe for hypothesis testing for the means in two independent groups. I've also put a copy of this in the document that I've posted on Blackboard with the other recipes for hypothesis testing. So the first two steps you've seen before. We set up our null and alternate hypotheses. The second step, you want to identify the two groups' sample statistics, so that the two different sample means, two different sample sizes, and two different sample variances. Then the fourth step is to calculate the pooled sample standard deviation. And you can see the formula there. As long as you have the information from step 3, straightforward to calculate that. You don't have to memorize any of these formulas, by the way. I know I've mentioned it before, but you know, the assignments are open book in that sense. There's no point in memorizing these formulas, and that's part of the reason why I'm providing these recipes here as well, as for you to use them. So the fifth step, you want to choose your desired alpha value, typically 0.05, and identify the degrees of freedom. Then you want to identify the critical value of the t-score for the rejection of the null hypothesis. So this is the exact same as what you've done for prior hypothesis testing that we went over in the second lecture. Again, you're taking the alpha value. If it's 0.05, you look up the t-score under 95% in the table. Depending on whether it's two-sided or one-sided, you choose the appropriate column. Get your degrees of freedom to triangulate to the appropriate row, and you'll find the critical value of t that you need for rejecting the null hypothesis. Once you got that critical value, your next step is to then compute the pooled t statistic using the formula that I'm showing there that I also showed on the prior slide. You get your pooled t stat. If it's greater than the critical value of t, then you reject your null hypothesis. With the caveat being that if your alternate hypothesis is left-sided, then you only reject the null hypothesis if the t statistic is less than the critical value of t, so it would be negative, right? Because you're looking for a left-sided, looking at the left side of the distribution. Okay, so let's walk through an example here. So let's say we have a sample of 337 participants in two independent groups in a clinical trial for coronary health improvement. And so they were randomized into these two groups, the intervention and control group. And we want to know if the mean age distribution is different in the two groups. Normally you want the age to be the same if they've been randomized, but here we're going to test it. So in group 1, the mean age is 50.39. In group 2, it's 50.83. And so our question is simply, are the ages significantly different between the two groups? So our null hypothesis, kind of the status quo, is that they're the same, right? Our alternate hypothesis is that the ages are different. And so this is a two-tailed hypothesis. So the next step is to collect the data on the two groups. So the sample size in group 1 is 167. We have the sample mean there of 50.39 and the standard deviation of 10.97. We have the same numbers for the second group, and our alpha value is 0.05. Total degrees of freedom is equal to the group 1 plus group 2, sample size minus 2, so we get 335. So we take that information, look up the critical value for the t statistic in the t table in your book. At a 0.05 and 335 degrees of freedom, the critical value is plus or minus 1.96. So the next step is to compute the pooled standard deviation. And I've shown the statistics there. You know, we plugged in the sample sizes of 167 minus 1 multiplied by the variance of 10.97. We add that to the same numbers for the second group, and then we divide it by the sample size minus 2. We get our pooled standard deviations, just plugging in the numbers from the formula on the last page of 11.05. So then to calculate the t statistic down below that, we take the mean of the second group subtracted from the mean of the first group, that's the numerator, In the denominator, we have that pooled standard deviation multiplied by the square root of 1 over 167 and 1 over 170, end result being negative 0.37. So that's our t statistic that was calculated, and that's less than the critical value of negative 1.96. It's less extreme. So that means we fail to reject the null hypothesis, right? It's in the middle of the distribution. It's not on one of the tails, so it's not significant at 0.05. We don't reject the null hypothesis, and we conclude that the ages are not significantly different between the two groups. So I'm not going to go into this in as much detail, but you can also construct, anytime you can do a hypothesis test, you can construct confidence intervals. And so these are going to be similar to confidence intervals you've seen previously, with the differences being that on each, you're going to subtract the mean of group 2 from the mean of group 1 on each side of the confidence interval, and then you're going to plug in your t statistics just like you've done previously. The difference now being the degrees of freedom will be based on the two groups, sample sizes minus 2. And then lastly, you multiply it by the standard error. And the standard error for x1 minus x2 is simply that pooled standard deviation multiplied by the square root of 1 over n1 plus 1 over n2, which was actually the denominator of the t-test that you calculated on the prior slide. And again, you just compute the left and right intervals and using the t-distribution score value like you did for hypothesis testing. All right, so all of this begs a question. Remember that third assumption where I said that the population variances needed to be equal? What happens if they're not equal? Well, then we have to conduct the t-test a little differently. And so that brings me to the F distribution and the F-test, because this can actually be used to test for equal variance to see if the variances are equal. Now, if they're very similar in number to each other, you probably don't need to do this test because they probably are equal. But you can do a formal hypothesis test for the equality of variances. And you would use the rejection region for the two-sided test. So the null hypothesis that I've shown there is that the variance in population 1 is equal to the variance in population 2. The alternate is that they're not equal. Well, of course, we don't have the populations. We have the samples, right? So how do you do an F-test? The F-test is simply a ratio of the sample variance in group 1 divided by the sample variance in group 2. So you can see that F ratio there. You put the largest sample variance in the numerator, though. So you always put whichever variance is bigger in the numerator. And that's your F statistic. Then what you want to do is see if that F statistic that you've computed is bigger than a critical value of F that you look up in the F table, which is also in your textbook, using whatever alpha level. Typically you would pick 0.05. And so you would look that up in the book. And the degrees of freedom, there are two different degrees of freedom that you actually use in the book. You got it's what I refer to as V1 and V2. And in this case, V1 and V2, you triangulate them on the table, are just N1 minus, so that's the sample size in group 1 minus 1, and then N2, the sample size in group 2 minus 1. So you use those two different degrees of freedom numbers for the F table. So the F statistic itself is not complicated to calculate, but the whole purpose of this is to figure out if the variances are not in fact equal. If they're not equal, then you need to use this complicated t statistic for comparing the means. It's actually not that complicated. It's the same as the previous one, except for two differences. The first difference is you don't have the pooled standard deviation in the denominator. Instead, you have those two sample variances under the square root sign. Second difference is degrees of freedom. You calculate pooled degrees of freedom for the t statistic with that formula. As long as you have the numbers, you can plug them in. It's just kind of a pain in the ass, frankly, when you look at that. You look at that formula. So this is why we have computers. Don't worry, I'm not going to make you do that on the homework. I'm not that mean. All right. So now we've made it through hypothesis testing for the difference in means in two groups, two independent groups, right? What if you want to compare means in 3 or more groups? Well, we can do that. So now we're testing the equality of 3 or more means. And we use a procedure you've probably heard of somewhere called ANOVA, analysis of variance. And so our null hypothesis here is that the mean in population mean in group 1 is equal to group 2, is equal to group 3, is equal to et cetera, all the way out to group J. Our alternate hypothesis is that one or more of these group population means is not equal to the others. So we don't know which one it is. We're just saying that they're all not equal to each other. That's our alternate hypothesis. Our null is that they're all the same. So like the t-test, ANOVA is referred to as a parametric procedure that has some important assumptions involving, as you would guess, like our other tests, independence, normality, and equality of variance. So the observations, we assume the observations in each group are independent. We assume the mean is normally distributed within each group, and that the variances of the underlying populations are equal. Note that when the sample size is large, due to the central limit theorem, so large being greater than or equal to 30, the normality assumption is less important because we can assume it. But the other assumptions still are important. So what's the intuition behind ANOVA? The basic intuition, the question we're asking is the among group variance estimate, so the variance between these groups, between or among these groups, is that variance greater than the within group variance estimate, so the amount of variance within each group? If it is, then that implies that the corresponding population means are in fact different. All differences among the sample means are combined into a single sample statistic in this test called the between group variance. And then that statistic is compared to the expected amount of random sampling variation within the groups called the within group variance, and we're using an F-test here. And so to test the null hypothesis that the population means are identical, we use the F-test statistic with the F distribution. So here's a look at the F distribution. So as you can tell, this is a distribution that ranges from 0 out to some positive value, right? And it has a mean that bunches up at 1. So whereas in the normal distribution, the mean bunches up at 0, on the F-test, it bunches up at 1. And then we have this long, skinny tail that extends out to positive values. And basically, what we're trying, if the null hypothesis is true, then the values are going to all bunch up somewhere around 1 on the F-test. If we want to reject the null hypothesis, though, we're looking for values that fall on this right tail, right? So our critical rejection region is we're going to look it up in the F table, and it's going to fall out on this right tail, a critical value somewhere greater than 2, because that's going to be the equivalent of alpha equal to 0.05, depending on what our alpha level is like. Anyway, I just wanted you to kind of have a picture in your mind of what the F distribution looks like. So in terms of, so there's some terms and formulas for computing this F-test. The basic rule is if the F statistic that you compute is greater than your critical value that you look up in the table for a given alpha level, then you reject the null hypothesis. You'll remember there are 2 different degrees of freedom for the F stat. I mentioned that in the previous discussion. And those are referred to as V1 and V2. And so the way we calculate those degrees of freedom are a little bit different in the case of ANOVA. And so I'm going to walk you through some of this thing. The F statistic itself is a ratio of, so on here it's referred to as MSA, the mean squared, between group variation divided by ms underscore e, the within group variation. So what are these things? How are we getting to these numbers? The between group variation, and you can see the arrow referencing it here on the slide, is equal to the explained sum of squares. And so this actually starts to become important when you think about regression. So it's the explained sum of squares. What is the explained sum of squares? The explained sum of squares is you're taking the mean for each group. So notation here, J refers to an individual group, right? You're taking the mean, overall mean for each group. You're subtracting out the mean, the overall mean, and you're squaring that. The error sum of square, so that is the explained sum of squares, and that goes into the denominator that goes into the numerator of the between group variation formula. In the denominator of that is simply j minus 1, the number of groups, minus 1. The within group variation, ms underscore e, is the error sum of squares divided by the total n altogether in the population, and then minus j, which is the number of groups. You're not going to have to memorize these formulas. Please don't worry about that. The error sum of squares is the difference between the total sum of squares and the explained sum of squares. The explained sum of squares, which you'll see at the top there, should look somewhat familiar to you because you've, in prior assignments, done the sum of squares. In this case, what makes it a little different is we have I observations in j groups. So, right, because we're not just looking, I is an individual observation, but we also have multiple groups. So you're subtracting the mean from each and every one of those observations across all the groups, taking, you're squaring it, and then you're taking the sum of that, basically. And so that's the total sum of squares. Anyway, long story short, if you have the total sum of squares, and if you have the total sum of squares, explained sum of squares, and error sum of squares. As you can see from the formula by the error sum of squares, as long as you have the total and the explained, you can figure out the error sum of squares. Once you have that information, then you can calculate the between group variation and the within group variation, the ms underscore a and the ms subscript e there. Once you got that information, then you can calculate the f-test. Another important thing is the degrees of freedom. So there are 2 different degrees of freedom numbers that you need to use the f-table. So for this particular formula, v1 is the first degree of freedom is j, the number of groups, minus 1. v2, the second degree of freedom number that you need is the total number, the big N, the total N of all the observations in the groups, minus j, the number of groups. Okay, so here's the recipe for testing for ANOVA. First thing is you set up your null and alternate hypotheses. The null is that all the means are equal. Alternate is that one of them isn't equal to the others. Then you identify your alpha level, say 0.05, the total n. So the big letter n here means the total number of observations across all the groups. The little n means the number of observations in a particular group. Secondly, you want to identify the number of groups, j, in each group, the sample size in each group, so that's the little n1, n2, n3. Next step, you will identify the critical value of f in the f table using your alpha level and your degrees of freedom. v1 equal to j minus 1, v2 equal to n minus j. If alpha is equal to 0.05, then you look up the f score under alpha equals 0.05 in the f table using the 2 degrees of freedom numbers to triangulate. Use v1 for degree of freedom 1 in the table and v2 for degree of freedom 2 to look up the f score in the appropriate row. Next, you want to identify your total sum of squares, SST, SSA, which is your explained sum of squares, and SSE, which is your error sum of squares. So in the problems, I'm going to provide those numbers for you. I'm not going to make you calculate those, but you will have to take those to calculate the MSA number and the MSE number, which is the mean sums. And you will take those to compute the F statistic in step number 6, which is really a ratio of the MSA to MSE. And then if that F statistic is greater than the critical value of F that you looked up in the table, then you just reject the null hypothesis. However, if you're, well, you'd actually, sorry, the last bullet there's a typo. Don't worry about whether the alternate hypothesis is left-sided, because here we're not interested in left or right-sided. We are just simply interested in whether the means are equal or not. So yeah, all you care about is whether the F statistic is greater than the critical value of F. If it is, then you reject the null hypothesis that the means are all equal.